branch in Dubai, and I'd like to welcome you on our presentation on fireproofing fundamentals. This is our second webinar series in a week-long series geared in educating, engaging, and empowering individuals in the industrial sector. Before we get started, a few housekeeping items. All audience members are muted during this call, but you may ask questions using Q&A function that is at the bottom of your screen. At the end of the presentation, we will answer a few questions from the audience. At the end of this session, a survey will pop up. If you have time, please let us know how we did. It would be great to get your feedback, and your response would ensure that we're providing the best possible content that is addressing your needs. I'd like to introduce our speaker, Tom Klein, Senior Director of Concrete Repair Solutions. Tom has been working over 40 years in structural repair and rehabilitation of concrete structures. He has experience in investigation, design, planning, and execution, having worked on over 1,500 individual projects. Tom manages and directs a diverse group of technical experts in providing design-build capabilities, developing turnkey repair strategies, and implementing sophisticated and verifiable repair programs for a wide range of concrete repair customers. Tom was also the original developer of the Plant Condition Management System over 20 years ago, which he will overview in today's call. With that, I'll pass it over to Tom. Thank you. Tom, it's all yours now.
Thank you, Heba, and I want to welcome everybody to this webinar on fireproofing strategies, which is a topic that's one of my favorites because there's so little put out there of public knowledge on fireproofing just in general, much less some of the agenda items that we'll be talking about. Those agenda items are going to include fundamentals and material selection because there are so many different types of fireproofing materials out there. What does the term rating mean and the types, short and long-term deterioration, and also how they're in use and what their service is pre-fire event. We'll talk about surveying and evaluating these structures that have fireproofing and repair strategies, as well as a typical case on the most commonly used fireproofing material in the world, which is cementitious materials, or primarily concrete. Now, we like to begin all of our meetings with a safety moment. And our safety moment for this series is obviously related to COVID-19. As a company, we're concerned for the health and well-being of our employees and our customers. We're implementing steps to ensure this daily, and many of them are outlined on this slide. With Safety First, Structural Technologies and its licensees are maintaining operations within guidelines set by the government. We are partnering with clients to safely continue work on critical projects and developing plans and schedules for deferred projects. Thanks for taking the time to listen to our safety moment. Now let's get started with the presentation. So what's the purpose of fireproofing? And it's pretty simple. It's maintaining that structural stability and the integrity of those structural members that are being protected. And it can be not only structural framing members, but also vessel and pipe supports that are conveying very critical processes. And there's a defined time for when it's exposed to a fire that we want it to stay integral and competent. The reason is we want to not only protect personnel that might be in a specific unit or plant facility, but we also want to protect those first responders that have to go in and knock down the fire event. So there are two different types of strategies when we start looking at fireproofing. We have active and passive forms. The active requires literally a response to activate the systems, and that can be things like a firewater deluge that has big, large monitors and are flooding down copious amounts of water to suppress the fire. or it can be a halon gas system, a suppression system, which is literally taking the oxygen out of the air. But these all require a response. The type that we're going to talk about today is primarily a passive strategy, and that involves a barrier coating, and it could be a barrier thickness, such as in concrete, or a thinner coating, such as in some intumescent. We'll talk about these different types of systems, but we're trying to protect that individual structural element or that vessel so from heat without any additional intervention, meaning that a button doesn't need to be pushed in order to activate it. And these passive fire protection systems, they're in all the markets, whether it's industrial power, municipal, commercial. They're all doing the same kinds of things, but what we'll see from this presentation, there is a difference between interior fire protection systems and exterior fire protection systems. That's primarily due to some of the environmental challenges. So what has really started to highlight these types of situations and fire scenarios really got activated. I mean, fireproofing has been around for well over 100 years, but where it really became key is during the Piper Alpha disaster, which happened on the North Sea, which was a rig, an oil production rig out in the North Sea, where 167 people out of 229 died. And it was primarily due to inactive deluge systems that required activation, and most of the sprinkler heads were already plugged. And what made it very tragic is that most of the people that died ran to these BRBs, these blast-resistant buildings, which also have 3-hour fire ratings, and they waited inside those structures. Unfortunately, the fire lasted much longer than 3 hours, and most of the people died because of smoke inhalation, not from the burn. So it was very tragic. The ones that did survive actually jumped, and it was, stay and fry, or, jump and try. So those were the monikers. So this was the initial one, and then the one that caused a lot of concern in the industry, and I'm a member of the National Fire Protection Association, was the attack on 9/11 to the Twin Towers. And during a very long and protracted investigation, it was seen that terrorists actually not only impacted the towers with a fuel-laden plane, but also that the fireproofing was probably inadequate that was put on some of the floor truss members. So again, that fireproofing called into question and can absolutely be a lifesaver. So when we look at the basics, we're really trying to put passive fireproofing on these members at a minimum thickness. And the reason we put it on at a minimum thickness, or we try to, and that's again after it's being tested, but we try to lower the dead load on the structures and the vessels, because obviously those loads still have got to be transmitted down through the element into the soil. So we do it for a minimum thickness of a particular material, and there's a bunch of different types. We try to restrict that heat transfer, and that's important because that's that heat that's coming from the outside, and we want to keep it from getting into that protected element. We know at some point it will because of thermal gradients, but we're trying to keep it as long as possible, and that's where we get our rating. And there's an acceptable steel core, and we're mainly talking about structural steel members and vessels that we're trying to protect. And it undergoes changes when it gets up to a certain temperature, and we'll talk about it in the next few slides. But essentially, we want to keep that so that it'll avoid collapse and buckling. So there's a few different types of fire testing methods out there. You'll see on this slide that there are two that are ASTM rated. One is very common in building construction, which is ASTM E119. That is not accepted in petroleum or petrochemical facilities anymore. It was years ago, but it's because the fires are primarily based off of cellulose materials, that don't burn nearly as hot as what we get with hydrocarbon pool fires. As such, we see that ASTM actually came up with a more robust test in the form of ASTM E1529, which has a rapid rise, and that's really what we're looking for, these rapid rise, because when hydrocarbon burn, it can get hot, essentially 2,000 degrees Fahrenheit within 5 minutes. And we'll see from some graphs that that'll be coming up, cellulose really never even gets that hot functionally. Now, what is accepted in the industry right now worldwide is essentially Underwriters Laboratory Test 1709, which is set up similar to ASTM 1529. There's a 30% higher heat load than with the 1709 versus the 1529. And what's special about these tests is it also evaluates the weathering and the effects of aging on systems. So to get a UL 1709 successful test result is very important for manufacturers of these fireproofing materials. And if you're a specifier and you're in the audience, the webinar audience, very important that you look to see that they have a UL 1709 rating on the fireproofing materials if it's going to be used in a petrochemical facility. So I was talking about these curves a little bit earlier, and it's important to see how differently hydrocarbon-fueled fires operate from cellulose. It takes much longer, and it doesn't get nearly as hot. Now, cellulose is very important because most things, building materials, are made of cellulose, but the hydrocarbon is very special, and we're showing just some standard hydrocarbons such as lube oils and crude. But when we get into jet fuels, it can rise much higher and much faster when we have very special volatile materials. So it's very important, especially for the firefighters, when it comes time to knock down the fire, especially if they're in a confined space such as a building, that they're aware of what they're entering when these fires kick off. Now, I talked about the temperature being important with structural steel members, and we're really looking at 1,000 degrees Fahrenheit as the go, no-go for the fire rating. And that's where there's a 50% reduction in strength, and we see that as important because that's when that structural steel member, and for testing it's a W10 by 49 that they use to standard test these products. But we're looking at a 50% reduction in strength, and that's what is believed in the industry as enough to cause buckling and or collapse. So that is how we get our fire rating, is the time to where that internal member reaches 1,000 degrees Fahrenheit, and how we do that in the testing procedures by thermocoupling the actual structural member itself. So the rating it's a function of time and ease of evacuation, that fire hazard posed by the substance, and then the fire suppression capabilities, meaning is there a certain time before first responders get there. Obviously, we want the personnel out of there, and we want to protect the first responders when it comes time to actually knock down the fire. And remember that these passive fireproofing materials, they don't extinguish the fire. And if the fire goes on longer than what they've been designed for, what will happen is you'll still get significant damage. And as you can see in the photo on the right, this is just showing some deteriorated, what we consider CUF, corrosion under fireproofing. That's a designation by NACE. 2 inches of dense concrete is going to provide about a 2-hour fire rating. 3 inches, 75 mm, is going to provide a 4-hour rating, and that's according to the American Petroleum Institute guideline, which is API 2218. So we try to also look at behavior with there's going to be a fire and explosion, and what that fireproofing needs to resist, and obviously thermal, but also erosive forces when we're talking about potentially having a jet fire where there's very high streams of heat hitting a particular member or vessel. What that surface temperature of the substrate is going to be, ultimately to make sure that that fireproofing is going to be able to bond during the event. Believe it or not, making sure the fireproofing is also non-combustible, because some of these materials, if they don't have adequate sealers placed on them, some of these lightweight cementitious materials, they can actually absorb hydrocarbons and actually be like a porous sponge if they're not adequately sealed, and can actually start on fire. And then obviously it needs to withstand explosion and subsequent drag pressures. What does that mean? That means if it's a large box furnace that's on top of some columns, we have an explosion within that, there's going to be a stimulus and a response, and we're talking nanoseconds, but with these explosion and drag pressures, literally cementitious materials that might be attached to the columns, if they're not adequately reinforced, can actually burst off of the member and no longer provide fire protection. Now, the pre-fire durability, I was talking earlier about weathering in some of the testing means and methods, chemical tolerance, especially in units that might have products that they're producing that can deteriorate the fireproofing materials, not just concrete, but also some of the other coatings and linings that they apply for fire resistance. It's got to be vibration resistant also in those regions that might have reciprocating compressors, those kinds of things. Also hardness, especially when we're talking about first level areas that might be impacted or nicked by skid steers or pallet jacks, and even a small nick or cut within, say, a intumescent coating reduces and is a hot spot during a fire event. So many of the specifications for brand new require essentially concrete as fireproofing on the first level, and then everything up from that turns out to be a much lighter weight material that can take the impact. Abrasion and erosion resistance important, especially when it comes time to knock down the fire. Some of the materials we'll talk about actually get engaged at high temperatures, but form a carbonaceous char. And if you hit it with a fire hose, the streaming itself can actually wash it off of the structural steel member. And if the fire reignites, it has no way of protecting the steel because the fireproofing material was essentially washed off. We'll talk a little bit more about bonding strength, especially with some of these coating materials such as intumescence need a incredibly strong bond so that when it essentially initiates, it's going to be well bonded and won't pop off. And obviously washdown resistance, especially in those areas that might have spills and things that we need to remove from the surface so it doesn't act as a flammable coating over top of a structural member. I indicated earlier also that there are many different types of passive fireproofing materials. The most common is cementitious, and it's because many of these older structures, that's what they had. They had concrete. We say three things about concrete. You know, it's pretty good in the, it's pretty good in the fire. It's the number one. Number two, nobody's going to steal it. Number three, it cracks. But we tried to work with those items, and concrete is a very good fireproofing material, hard and durable, and it's economic and very easy to install. Very similar type of means and methods that you'd use with formwork and placement and/or spray applied if it's going to be like a shotcrete material. Now, the intumescents, they're relatively new on the scene, but they've been around for, at least 30 to 40 years, came over from Europe, I know, to the U.S. At that time. What's nice, it forms that carbonaceous char, has excellent corrosion resistance for the structural steel because it's really protecting it. And a big problem with cementitious materials is this corrosion under fireproofing, the CUF. When an intumescent is applied, we can actually see if there's embedded or if there's steel corrosion of the structural steel members underneath. It'll actually start bubbling up and you can see it, where you don't see it with the cementitious materials until many times it's too late. There are other types of products, endothermic blankets, boards that are literally cut to fit, these inorganic boards. There's also indoor applications with sprayed fiber reinforced materials, fire-resistant materials. And then there's also composite panels, and these are very specialized. They're typically put onto, type of noise-resistant cabinets that more critical equipment put in. They're built by cabinet makers. they're typically not installed out in the field except associated with sophisticated and important critical equipment in the plants. So when we talk about the SFRMs, they have aggregates and fibers conveyed through a hose and mixed, and typically it's sprayed on, as the name implies. And they could be a lot of different types of products. The intumescents are included in this, and the lightweight cementitious materials, which can include also even lightweight concretes. When we look at the cementitious concrete materials, which is the most common, they can be made with a lot of different types of cements, including Portland, but they're also geopolymers, and then modified fire-resistant cements. We're talking about calcium aluminates, those kinds of things. And when we classify these cementitious fireproofing materials, specifically when it's related to concrete, we either go dense or lightweight, with the dense being with the numbers there. I just used the English nomenclature, but it's, I should say American, 140 to 150 pounds per cubic foot versus the lightweight 25 to 80 pounds per cubic foot. What's interesting about that is the thermal conductivity tends to be inversely proportional to the weight, meaning that the lightweight concrete typically performs better in a fire test than the dense concrete, and that's because there's more porosity that's locked into the cementitious matrix or the cement paste. And with that porosity, that means air, and then that air is going to act as an insulator, which is terrific. Now, what's great about these cementitious materials, they can take the flame impingement up to 2,000 degrees Fahrenheit, which is our hydrocarbon pool fire. So it works out very well, and depending on the thickness, we can get the different hour ratings, and it provides another protective film to the embedded steel. Also, this alkalinity that's in cementitious materials, with that alkalinity, it provides passivity to the steel members that are encasing it. The only time it becomes an issue is when that alkaline conditions change to carbonation, where we can actually have a lowering of that alkalinity, but that's usually at a much later date. So where do we find concrete fireproofing? We find it in process units, multi-level equipment structures, pipe racks. It's very similar to what you would say, where do we find concrete? And we find it all over the world. So we see that it's in a lot of different regions, and it does during a fire scenario, is that specific surfaces of a member, and concrete's very forgiving. It's hygroscopic, so it freely gives up the excess water. There's always excess water in the matrix of concrete. It's called moisture of convenience. Well, that water wants to go and cool off the surface. Now, as it's migrating through the capillaries and the pore structure of the concrete, it takes with it in solution soluble salts. And these salts then are in solution with the water. It's migrating to the concrete, and it wants to cool that surface. But at some point, because there's isotherms, different varying levels of heat within the concrete, they precipitate out. And as you can see from the dashed line there, that's where we start getting a boundary. Now, there's boundary forms after there's a significant amount of the salts that crystallize and then essentially pore block and don't allow any more moisture out. The concrete still wants to give of itself, and moisture continues coming out of that concrete mass, and it can't go any further. And then what happens is that moisture then turns to steam and then jettisons out or spalls the concrete. And we have anecdotal evidence from fires where we can actually see those surfaces are white with crystalline salt products. It's also known as efflorescence and a bunch of other things, but a lot of it is calcium carbonate, and you see that just by anecdotal evidence. That's why it's so important when it comes time to do repairs on cementitious fireproofing. You have to go all the way around 360 degrees circumference of the member. You can't just patch because of the amount of salts in the pores. So what will happen the next time there's a fire event, that moisture is going to want to try to get out again, and that new repair you put on will also be jettisoned off. And there's been many instances where firefighters have been injured by patch repairs that were performed just right over top of a previous fire damaged area. So probably, as I indicated earlier, the most prolific thing that you'll see on the internet is the idea of having intumescence as fireproofing products. Does a lot of terrific things. They're lighter weight typically, and you can see corrosion of the embedded structural steel should that happen at a later date. There's a couple of different types. There's solvent-based, which is the older technology that's primarily used for exterior applications, and the reason is because the solvent-based intumescence, they produce a noxious and/or toxic gas as soon as they start to char, and this toxic gas can actually kill the people within area of any of these initiating intumescence, and that's why they had to come up with another version of this, which are water-based, especially for these big department stores and that kind of thing. So if there is a fire, it can still protect critical structural members, but it's not going to give off harmful or toxic gases that form this intumescent char. Unfortunately, those aren't good for exterior areas because they're not tolerant to humidity. They'll absorb water and or low temperatures, especially in those northern regions. They're typically applied via spray equipment, so pretty straightforward, but you have to have excellent craftsmanship, and the people typically have to be certified who are installing them. Smaller areas, obviously rolled, brushed, or troweled, so they work similar to many of the cementitious materials that have to be applied in the field when you can't form it up. So they're washable. What's great is you can get them in different colors, and you can get them where they're mark resistant, meaning graffiti. So that's terrific, especially in public areas. They're protecting that steel. NACE had an acronym for many years, corrosion under insulation, primarily related to piping under insulation. But because of the damage that's worldwide, NACE came up with another acronym, CUF. This is corrosion under fireproofing. So what's great is it is prepared as a coating, a protective coating to be placed over top of the structural steel, so more surface preparation, that kind of thing. Also, if there is corrosion that's happening underneath the system, you'll be able to see it on the outside. It'll actually start bubbling. As I indicated, it's required to have that applicator certification. And another downside to it is it's generally higher in cost when it's compared to cementitious materials. So it's literally weighing the pros and cons with these systems. Now, how does it work? And because that's always the biggest thing, and probably the secret sauce that nobody seems to understand about these products is that it's got to get really hot, much hotter than anything that would be in a standard process. So we're looking, 200 to 250 C or well over 400 degrees Fahrenheit. What happens, there's a resin within the matrix that melts, and as it melts, it's also starting to generate a gas, and this gas then forms it's called a multicellular insulating blanket. Essentially what it is, it's non-interconnected bubbles that are inside and forming this insulating material. And but it limits that spread of the fire, but it doesn't put it out. Like I said, none of these passive systems puts out fire. Now, if we looked at these intumescence under an electron microscope, what you're looking at to the right side is a whole bunch of different structures. And it's interesting to note because how many of these manufacturers are able to get through some of the patents is because they change the resin types and they change the fiber types. And it does make a change to the substructure. Now, these are very high, power microscopy in order for us to take a look at these. But they all have something in common, which is to have fibers in it, so that when it does expand, and we're talking 15 to 40 times, it's still going to hold it together and it's not going to flake off. So discussing that, we know that everything deteriorates, and we're very concerned when we're talking about fireproofing deterioration because it's all associated with risk. And this also is how underwriters with insurance companies are also looking at it. Believe it or not, much of our work is initiated by essentially correspondence from insurance companies that have cited, a client of theirs for having something at risk, and they don't have a system in place to evaluate it. As Eva indicated earlier, we developed a system known as the Plant Condition Management System that specifically looks at, all of these kinds of civil assets. And then there's a adjunct to that, which is the American Petroleum Institute's Guide 2218, which also helps classify and put together a program for repair. So we're taking cementitious concrete as an example, showing some of the deterioration mechanisms, because it is the most common worldwide. We take a look at the embedded member and potential cracking. As I indicated earlier, we say those three things about concrete, and cracking is one of them. Also, these fireproofing materials are typically very lightly reinforced when we're talking about concrete around these members. Typically, they have a 2-inch by 2-inch mesh, or 50 mm by 50 mm galvanized mesh that is then studded and attached to the steel member. But what can happen over time is we get cracking. It's a direct conduit to the outside, allowing moisture and oxygen to get to that embedded structural steel member, and then that results in corrosion. Now, when we say corrosion, this is just a photo from, an investigation I did down on the Gulf Coast in the U.S., but this is very typical, where we see the fireproofing having been compromised over many years, lack of maintenance by the in-house maintenance forces because they didn't know what to do or even how to evaluate how bad is bad. But you can see the laminations. What's really important is that much of this fireproofing also becomes a falling hazard because it's elevated, and when we start having falling concrete hazards, it becomes a real issue for not only personnel protection but also for equipment protection. We're looking right now at a picture showing two beams that are of identical construction, but they're right next to each other, but they're in very different states of embedded structural member corrosion. You see towards the bottom of the slide, we see very large gaps, and we know that's actually wedging itself off of the underside of the bottom flange, and that's ready to fall, but yet the member next to it is just showing some very small indication that it's also following that same process, but very early in the process. We're starting to see some of the steel corrosion starting to emanate through some of the cracks and potential conduits that are from the base of the cementitious concrete. Now, this is a photo actually that was caused by improper detailing, but also improper construction of the cementitious concrete. Fireproofing, you can see up top of the slide where the slide bearings on this heat exchanger literally have been seized with elevated placement of the fireproofing. There's actually slotted bolt locations that would allow this to move, but it can't move because the fireproofing is in the way of the essentially the slide pads. And what you'll also note is there isn't any mesh reinforcement that we would want in that particular location. So essentially, this fireproofing is ineffectual and is not going to work. I actually took that little spanner wrench down there and just tapped on it, and that whole side fell off, where the owner said, "Hey, stop doing that." But I said, "No, you got a bigger problem than me just tapping the sides of your fireproofing." So we had some very in-depth discussions and further investigations of the structure based on what we found just through this portion. And they kept on patching it over and over again, thinking that that was going to take care of it. You can see some of the waterproofing materials at the top. They really didn't understand the root cause, especially as it relates to failure of the fireproofing. We also see that there can be many things that are embedded within the concrete that are critical for corrosion. The photo to the right is showing riveted connections. This very old structure back from the 1920s that was built. This is in the Gulf Coast, but you can still see some of the remnants of the embedded mesh there. And unfortunately, when I tapped those rivet heads, actually the rivet heads started popping off, and that obviously is a friction connection and you know, a shear connection with the rivets in place. So that was a big problem, but obviously we found you know, this was allowing the owner to make a risk assessment. Now the picture to the left is showing, yes, indeed, it had you know, embedded wire, but also a lot of, well, it had a lack of consolidation around it, a lot of honeycombing or rocks without cement paste. So that deteriorated very quickly, and you can see the flanges actually starting to corrode with that, and obviously not providing any fire protection. Now, we do see some of these inorganic panels and even masonry that's used as fireproofing. Unfortunately, what we see with these kind of boxed out regions is that the areas within these boxes that are sealed, essentially the humidity will go to 100%, because when we open them up, we see condensation on all the surfaces. We see significant rust. The photo to the right actually is showing a masonry column that originally had a steel column in it, but and this had been built in the 1930s for a very old refinery in the U.S., and we found that the steel beam, or the steel column, actually had no base to it anymore because it had totally corroded, and literally the masonry was holding up the pipe rack. So it was very serious, and we immediately had to shore those regions based on our inspection and some of the inspection excavations we did. So we also see other things that are process related that can damage the fireproofing. This particular one is showing a pipe shoe on top of a pipe rack beam. And you can see over the years it's been repaired several times, meaning that they didn't address the root cause. It's been painted. And essentially they had the steel beam actually located higher up into the fireproof section. And it was put there on purpose, not so much that it would be protected by the fire, but that the pipe shoe could run over top of it. Unfortunately, and these pipes would move in and out with process streams, and unfortunately it corroded and seized up. It started galling, and because of that it froze, and then it started rotating the concrete, and we started having breakage on both sides. We had to understand the root cause, and the root cause was the seizing up, so we came up with a new system to actually put a half-round steel bar and then have the pipe shoe run on top of that half-round instead of fully flat on that embedded steel beam. But becomes a big problem, and we see this quite frequently in older refineries and chemical plants where they have the steel beams with the flange exposed. As you can imagine, that exposed flange is also subject to atmospheric corrosion. So a lot of fireproofing are also on some kind of unique geometric structures such as spheres, and primarily the pipe columns that are tangentially welded to the spheres. And you can see here's a customer who actually took a painstaking amount of time to seal all the cracking. Probably would have been a lot better to just put an elastomeric coating over top of it to protect it. But when we got to the top of this type of pipe column, we found that they had originally removed the rain gutter, and you can see that from the weld parts, the stitch welding remnants there. And so water was coming right off the sphere and then down on the leg and then going right into that annulus between the cementitious materials that had been tapered and then running straight down the leg and then causing corrosion. So we knew we had to remove that section or put a new rain gutter, which goes all the way around the member to keep rainwater from going down into that annulus. So when we look at these structures, and you can see that with fireproofing, many times the diagonal members don't have to be fireproof, so you can see that readily there. They're not fireproof, but you can see the amount of damage in the pipe columns here, especially with the corrosion emerging from a lot of the cracking. but how much is there? So the only way we can really tell is by doing these limited excavations. They're typically, 6 inches by 6 inches, so we can get in there. And what's interesting, you can tell from this photo, in excavation, we can see areas that had corrosion very defined at certain levels. The region above it is almost pristine. The steel is uncorroded. Even there's still galvanizing on the mesh that's within the fireproofing. But as soon as you get to the lower line, you see the pitting corrosion, and the galvanizing is off, and even the mesh is missing in many regions. So these excavations are important, especially when we want to try to get an idea about the remaining thickness and competency of the structural steel member that's supporting the vessel. What you might imagine from seeing this, you see the efflorescence coming out. You know there's moisture travel. This is at the base of a column. You see the calcium carbonate coming out. That's when the moisture mixes and commingles with the calcium silicon hydrate, which is the glue that holds the concrete together. It emerges. It's calcium. If you were to taste that, I don't recommend, but if you were, it'd be very tart. So it's salt-free line. But what you don't see here is a lot of steel corrosion of products, meaning rusting. So that's telling us maybe we're early in the curve, but it definitely needs to be addressed, and that moisture is emanating from much higher in elevation. So we do this by condition surveys and evaluations. We need to understand the cause of the distress and provide conceptual repair recommendations. Just to give an idea, this is a specific sphere like what we were just showing previously. We map the cracking. We then identify those locations for taking some excavation. And it doesn't have to be just on a sphere. It can be on individual structural elements, both horizontal and vertical. Again, we need to get to that single side. We're taking specimens out so that we can understand the pH of the material. I indicated that earlier through the process of carbonation. pH typically for brand new concrete is between 12 and 13. As it drops just during service, as soon as it gets below what we consider 10 or 9.8, it can be an active participant in the corrosion process. So we do some limited testing. We also do more specific testing in the field when we're trying to get an idea about the remaining thickness of the structural members. And when we do that, we're comparing the theoretical, what was in the original design drawings versus the measured, and then calculate the section loss and whether that's a critical member as defined by a structural engineer or something that has some safety factor associated. This particular photo is actually one that's off the internet. It was a very spectacular failure. Unfortunately, one individual was killed, another in very serious condition. They were inspectors. Believe it or not, this was during a testing exercise where they filled it. They hydro-tested it up to 80% of its capacity. And that hydro-test is actually heavier than its service loads. And what happened, even though the fireproofing looked great on the outside and it was regularly painted and everything, what they didn't understand was the corroding pipe columns underneath, and that essentially just failed and sat itself down. So very spectacular failure, but very tragic. So for a conclusion, and the need for fireproofing restoration, we always recommend that not only the PCMS, which is our plant condition management system, survey be done where we can take a look at literally hundreds, if not thousands of assets, but also applying it to API 2218. And it's important because that's going to help determine the fireproofing needs, and that's based on the processes in the area. Now, you can have a civil engineer go out and take a look at your structural assets, and we're very good structural engineers and contractors, but you really need to have a process engineer or the owner on the same route as you're looking at these structures to see if, in fact, you need the fireproofing, like what's being shown in that photograph. There are some diagonal members, and because it's not in an area that's highly volatile, we were able to just take off that fireproofing, blast the steel, and then coat it, and it didn't have to have fireproofing reapplied. So fireproofing was put there when it really didn't need to be. So that API 218 process and surveys very important because it can definitely save money, but also identify those areas that should have fireproofing and don't currently, because safety is key, and we want to make sure that we're minimizing the potential of structural collapse, especially during a fire event, and make sure that the personnel that are operating there aren't at risk from falling concrete hazards, especially in the potential of very dense structures where we can have a ricochet effect, and also critical equipment. Obviously, it also helps lower our insurance costs and the aesthetics, obviously, of damage or falling fireproofing. It can look quite terrible. So that's where we're at and our next steps. And I always like to leave the last slide to indicate that we have representatives in the region, with Ahmed being in the UAE and with Redwan in the kingdom. So at that point, Heba, I definitely am ready for some questions.
Well, Tom, thank you. Before we get into the question and answers, I'd like to remind everyone to please fill out the short survey at the end. Many people have asked for the copy of the presentation. We will not be distributing the content or placing online, but please feel free to contact us to request a similar presentation on or other topics for your team, facility, or company. We will also be offering additional webinars in the future. If you're not signed up already, we have 2 additional webinars this week. The first question, Tom, is what is the best inspection methods to inspect corrosion under the fireproofing CUF?
Wow, that is a terrific question, and I get asked that every single time I do this presentation, and that's very, very intuitive. And there are devices out there that make claims that they can detect through eddy current technology the presence of corrosion. So my issue with that is that they may detect that there may be some light rust on the structural members, but what they can't tell is what is the significance of that light rust, because sometimes that can be very, very minimal. Absolutely. What we always recommend is truth and verification, and we take representative inspection windows. As I indicated, typically they're 6 inches by 6 inches, but we take these representative windows at various locations, and we then test non-destructively with, with a UT meter, ultrasonic testing meter, so that we can get the thicknesses. Now, it's important to also have some type of reference in the form of the original instruction drawings so that we can tell what that thickness should have been originally designed for. And then what is the current measurement, and then what's that percentage, theoretical versus in situ, and whether we have a problem. But that's a very good point. There are technologies, I've seen some of them at the trade shows, but when I've taken a deeper dive with them, they definitely can only speak to that there may be some ongoing corrosion, but they have no idea how bad the corrosion is. So we always recommend truth and verification in the form of these windows. But a great question.
Thank you, Tom. Another question someone asked, at what temperature during fire does an RC member fail?
Does a reinforced concrete member fail? Is that the RC?
Yes.
Yes. Okay. Again, a great question. And the best answer to that is it depends. And it depends primarily on the reinforced concrete cover. Now, if it's in a very aggressive area where we might recommend according to code, and when I'm talking code, I'm talking about the American Concrete Institute code 318, which is the building code. But if it's in a very aggressive area, there might be 3 inches of 3 inches of concrete cover recommended, and that's also if it's in contact with the earth or in high sulfate areas. That's going to give you at least 3 hours of protection. that 3 inches before it's going to, uncover the steel. Now, the steel bars, what happens during that period of time, the steel bars are better conductors, as you might imagine, of heat. And the steel bars will take the heat further into the concrete mass. So, believe it or not, we see far more damage on massive concrete structures because there's large amounts of bars, especially in the exterior regions, that then hook into the mass of the concrete, and that heat goes deeper in versus very thin members or relatively thin members versus the mass concrete members that we see, damage may not be nearly as severe. Now, there's always, and I'm going to be giving a presentation in the next couple of weeks just on fire damage concrete and how we evaluate it that will more appropriately answer your question. But the thing is, you're looking at least 3 hours before any specific damage, and that's a petrochemical fueled fire. Now, again, as I indicate, all of these structures are designed differently, and it's the amount of steel in the member and whether it's a column or a beam. Obviously, a column is going to have a situation in a vertical orientation for racking, that kind of thing, where a beam might undergo torsion. And it's also related to the other members that may be attached to these specific structural elements. And when I say other members, I mean things like steel beams that are not fireproofed, that might be connected to a reinforced concrete member. And then that has a significant amount of growth during thermodynamic growth during the fire itself, and may cause additional damages that are related to the fire but not specific to the heat penetrating into the concrete mass. So I'm not going to say that the reinforced concrete member is going to fail in 3 hours, but we know the concrete cover is going to be consumed. And when I say consumed, I mean that it's going to extensively crack in rectilinear patterns. So it's going to crack and remove the aggregate to paste bond. The paste is going to modify, and with that modification, we have desiccation. And desiccation means even finer cracks, but on a microscopic level. So it's going to be consumed after that 3 hour period of time, and you're going to see spalling, and you're going to see exposed reinforcing steel. Now, also during this presentation that I'll be giving on fire damage concrete, there are different things that happen to steel, and primarily the metallurgy, and the way that we put out the fires are important, such as rapid quenching of the steel by fire suppressive efforts using fire water can do a lot of damage to the steel, which we want the fire to be put down, but from a metallurgical standpoint, it does a lot of damage to the steel. But we want to put the fire down, but understand that it's going to cause some embrittlement of the steel, and many times exposed steel, as a matter of fact, we do augmentation and place additional bars where there's exposed steel, because we have done some in situ testing that have told us, okay, there's some metallurgical changes and there won't be as much ductility anymore with those exposed bars. So reinforced concrete, depending on its design, we know at least you're going to get at least 3 hours due to the cover. So it's a long-winded answer, but there's a lot more to it, and that's a whole different discussion. But great question. I love those questions.
Just adding to this, to the reinforced concrete, does increasing the strength somehow give it more longer protection time? I mean, like during fire?
That's another great question, and another good one, because as we're increasing the strength of the concrete, we're literally increasing its density typically. Okay, we're adding cement content, we're putting in fly ash, we're doing a lot of things. Now, what happens with density, as I indicated, it's inversely proportional to its performance during a fire event, meaning actually concrete that are lower in weight and not as dense will perform better in a fire test. So you could have a and I off the top of my head, I can't do the MPa conversion, but say we have 6,000 psi concrete, which is fairly high strength concrete, versus a 3,000 psi concrete, but happens to be lighter weight materials, but still quality, has a good water cement ratio, just happens to be lighter weight. That's going to perform better, believe it or not, in a fire than the higher strength, more dense concrete. So great question. Now, another thing to understand is also the reinforcing systems. The pre-stressing, if there's pre-stressing in these structures, we've got some other issues because the pre-stressing, what will happen is there's going to be releases and relaxation of the pre-stressing typically during the fire events. And we see this many, many times, not only anecdotally, but you can do it by analysis, but it's more critical. And there's going to be essentially less ductility because you have less mild reinforcement in pre-stressed, precast members. And I mean pre-stressing, not just precast, but pre-stressed members. And since there's less, conventional reinforcement, there's less ductility during a fire event, and that means that the failure of the structural item could be more catastrophic with a pre-stressed member in a fire versus a reinforced concrete. But it can be designed. That's the thing, especially for fire codes. They'll put in additional conventional steel, especially when there's the potential with like in residential communities, those kinds of things.
Well,
great question.
Does fiber reinforced concrete offer more protection against fire compared to conventional concrete?
Another great question. Believe it or not, there's been a ton of research on this. I get all excited about this, so excuse my passion, but there's been a ton of research, especially here in the United States by the Southwest Research Institute based out of San Antonio, Texas, which is funded by the major petroleum manufacturers, producers, and downstream, where it's interesting. I'm not talking about steel fibers. I'm talking about polyethylene fibers, where they are requiring and specifying plastic fibers being incorporated into any lightweight concrete fireproofing that's placed on rigs out in the ocean. And not only because of the weight associated with it, but they have done through testing and have found that the placement of these plastic fibers, when it's subjected to heat, the fibers themselves melt within the concrete and then form these previous channels, meaning the relic indicators of where it once was, because the plastic melts away. So there's additional essentially cavities within the concrete, very fine because these fibers are very fine, but they're well distributed throughout the concrete mixture, and it provides additional insulating value. So that has something that's a great question, and it's something that has been proven through research, and primarily as it's being funded by the petroleum producers and downstream manufacturers and refiners.
All right. Well, another question is pre-stressed and post-tension member more vulnerable under fire without any additional fire protection measures?
Yes, they're more vulnerable, just as I indicated earlier. So there has to be additional means and methods taken as they are provided in the code, additional concrete cover, and then additional mild reinforcing steel placed within the member to provide protection during a fire event. As I indicated, there's a tendency for relaxation, so they're losing their stress. As we understand, the reason with post-tensioning and pre-stressing is to provide compression on the member so that we can have smaller amounts. We know concrete's very strong in compression, very weak in tension, so we're trying to remove a lot of the tensile forces on the member so it's able to make them thinner and smaller. The issue is with the fire, it detensions them, essentially, so we lose that amount of compression. So the members are more susceptible to, load failure. And we see this often. So as long as there's additional mild reinforcement that's placed in there, so that when the member does fail, it will fail ductily, meaning it'll be very slow and gradual, like a reinforced concrete member that's conventionally reinforced would be able to handle it. That's a great question. That's another reason why we want to have substantial grout plugs in the anchorage pockets, so that it's going to protect those wedge anchors and that cut-off edge of the strand that's used in post-tensioning. So very important, and that's a lot of times a detail that's missed at the ending of construction of a precast region. They end up just putting a sealant or something like that that's not fire rated. So we always recommend make sure that you're putting an adequate grout plug that's going to be able to take the fire, because that's a very important area, especially in post-tensioning on monostrand post-tensioning that allows the strand to move within the mass of the concrete. And if those wedge anchors fail, we lose post-tensioning in that location during a fire. It can be very serious, especially if there are firefighters trying to knock down and they're on specific floors where this might happen. Great question.
Very much, Tom. To all those who asked questions, please note that we reply via email to all your questions since we don't have enough time. Tom and I appreciate your input, and we'd like to thank everyone for attending today's webinar. Just a quick reminder, this is a week-long event, and tomorrow we'll be discussing improving reliability with equipment foundation repair with Michael Gullah. Please don't forget to complete a brief survey before logging out today, and thanks for your participation and input. Ramadan Kareem, everyone. Have a great evening. We'll see you tomorrow. Stay safe and productive. Bye for now.
Thank you, everyone, for attending, and stay safe. Take care.